Right, so we were contemplating trying to prove the positive energy theorem, and we had found some formulae that looked like mass equals the integral of a vector field over space like infinity, and that equaled something to do with k and curvature, or perhaps derivatives. This should be in inverted commas. It's simply dimensionally what you'd expect, integrated over a space-like surface. Arrange the indices at your convenience. You don't really need to know what the indices are to worry about this. If you expect this thing to be positive, it is reasonably clear you don't stand a chance of succeeding. If k is a vector, for the very simple reason that it's linear in k. How can something linear in k ever end up being positive? It's very hard. So the only real solution to this problem is to say, well, how do you manage to find something which is quadratic in something that ends up giving you a vector? Now we all know the answer to this, and the answer is that you think of spinors. So suppose that you had, just in Minkowski space, a vector k, and you thought you wanted to write it as a square of something. You would all say, well, of course, what you'd do is you'd write it like this, where psi was some kind of spinor field. Then, of course, you see you get the right kind of thing. This kind of thing could look like grad psi squared. It's got the right dimension, and it would be more or less positive. So you do stand a chance of getting the right thing, provided you're willing to open your mind to the possibility that there are spinors in the world as opposed to just vectors and tensors. We all know that there are spinors in the world, but my guess is that Dr. Stewart did not tell you how to deal with them. Is that correct? Okay. So having said that, we have to look at the question of how to define spinors in general relativity. So the very first thing that we need to do is to think about what is meant by the term spinor. You would probably say, in Minkowski space, that a spinor was something that transformed like the spin representation of the Lorentz group. That would be completely reasonable. So how does one recognize such a thing? So this is just in Minkowski space at the moment. So we all recognize that as being a statement of what's meant by a spinor, I hope. What does that mean mathematically? Well, let's suppose that we have Minkowski space with metric eta mu nu. Meaning diagonal minus plus plus plus. I have used Greek indices here for a very simple reason, which will become apparent. I have not made some kind of confusion over conventions. I really mean Greek indices here. So starting with the Minkowski space metric, the first thing you would do is to construct the gamma matrices, or Clifford algebra associated with 031. These are gamma mu. They are defined by an anti-commutation rule. Gamma mu is equal to 2 eta mu nu times the unit matrix. And because we're interested in the Dirac representation, these are 4x4 matrices. We could have picked a different representation, but we're not going to. So that's not unusual. Then, in this language, the generators of the appropriate representation of the Lorentz group are proportional to what I will call gamma mu nu. Gamma mu nu is just a half of the commutator of two gamma matrices, and the constant of proportionality is 1/2. So these are the generators of the Lorentz group, and you can check that if you start commuting these things, you do get the right commutation rules for the Lorentz group. How then do you recognize a spinor? It's got to transform in the correct way under a Lorentz transformation. So let's consider a Lorentz transformation lambda. It will have two space-time indices, lambda mu nu. It has the property that lambda mu nu, lambda rho sigma, eta nu rho equals eta nu sigma. That is to say, the Lorentz transformation preserves the Minkowski space metric. Now we can ask, how do we recognize a spinor? A spinor field psi will be a function of position. And if you make a Lorentz transformation, it will go to psi prime of x prime, which is equal to, with x prime equal to lambda x, and this is equal to infinitesimally, let's write it like this, s of lambda psi of x, where this thing is 1 plus 1/4 of gamma mu nu lambda mu nu plus ... acting on psi. And that's how you'd recognize a spinor in Minkowski space. These indices are raised and lowered with respect to the metric eta mu nu. So that's fine. Where am I missing an x prime? Oh, here. So, that's how we would know we were dealing with spinor fields. Of course, we don't have, at first sight, the Minkowski space metric to deal with. But we have something that is almost as good. In space-time, you have the space-time metric GAB. So here you can think of the space-time as being something like this. At each point in space-time, you know that you can construct a locally inertial coordinate system where the metric is the same as Minkowski space. So here, there is always a local inertial frame. Before I go any further, there's something I need to do about gamma matrices, I forgot. Because my signature is minus plus plus plus, I need to remind you of the fact that gamma 0 is anti-Hermitian and gamma space is Hermitian. Unless I tell you that now, it will cause trouble. So, space-time metric, GAB, at each point in the space-time you can construct a local inertial frame where the metric is indistinguishable from that of Minkowski space. It is locally flat. So I can certainly always manage to have some contact with what happens in Minkowski space. Now, for a general space-time, you know that the way in which you construct the local inertial coordinates is to consider coordinate transformations. So xa goes to x prime of a, which is some function of, well, a prime, which is some function of the old x's. Under such a transformation, since the metric transforms as a tensor, this will go to a new metric, g prime ab, which is equal to a prime, a, b, b prime, g, a prime. Actually, probably should put the primes the other way around. Because the thing transforms as a tensor, where this is the matrix of partial derivatives. That's just the tensor transformation rule. And what you know about local coordinates is that there is always an A such that G prime can be chosen to be the Minkowski space metric.
In the denominator.
Prime.
Yeah.
Yes. Such that G prime is the Minkowski space metric at a point.
Is that still true in the presence of singularities?
No, absolutely not. Singularities mess this up. You cannot construct locally inertial coordinates at singularities. I do not know what to do about singularities.
Very, very close to singularity.
Very close to a singularity, you can do it. Just not at one. Of course, in a coordinate singularity, it's fine, because this is how you know that the difference between a coordinate singularity and a, I was going to say an honest singularity, but it's not clear that that has any meaning. This only works at a point. Of course, you can do it at each point separately, if you wanted to, but that's not what I want to do. So I want to consider the following trick. I know that there will always be matrices A such that this is true. So the following is always true. Globally, meaning everywhere, I can always construct analogues of these matrices such that help if I got it right. It's just that if I do that, so I construct these matrices E, these are analogues of these matrices A, but they will no longer be of this form. So this thing basically constructs a Minkowski space metric at each point. They are no longer of the form dxa by dx prime, well, anything. They're not going to be of that form, they're just things which you can construct in this abstract way. They obviously will be functions of position. This is a function of position, but this is the same everywhere. These objects EA mu are known variously as. Well, if we were 20th century relativists, we would probably call EA mu the veilbein, from the German for four legs. However, towards the end of the 20th century, this became increasingly and utterly irrelevant because fear, of course, being four, dimensionality tended to become a rather more fluid concept. And so, typically, this got replaced by n-bein, n being the German word for whatever dimension you are in. Sometimes it was also called the veilbein if you were in a position like 11 dimensions where you tended to lose count. Veil being many. Now that's a physicist language for these things, but mathematicians have no such inhibitions and are not stuck in dimension 4 or indeed any other dimension, and they would call them frame fields, which is probably a bit more sane. So, at each point, these frame fields essentially allow you to construct the metric on Minkowski space. So that's very nice. That means that there is always a map between some particular metric at each point in space-time and Minkowski space. So that is what we're going to exploit to recognize the fact that there are spinors.
What types of conditions on the topology that allow you to have a spin?
On the assumption that it really is a manifold, so there's a problem with singularities and such like, the answer is for sure orientable.
But if it's not simply connected, can you actually make them continuous?
You probably not, but you can patch things together in such a way that there is no problem, up to ambiguities of a kind which I am not going to specify. But they're like gauge ambiguities in electromagnetism. So they're not really serious ambiguities. Well, I think probably at some level, the honest answer to that is probably not really understood, but they are basically like gauge fields. So they can transform in exactly the same way, and there are topological problems associated with the definition of frame fields. But at least as far as doing things locally, and that's all we're going to do, we will not encounter problems, and we are not going to encounter problems in anything we do. There is another, to be more precise, there is a different topological classification which really has to do with the existence of spinor fields, and I think it must be the same thing as the existence of frame fields. The first Stiefel-Whitney class must vanish. However, there's always a way around it.
Is that sufficient and necessary?
Yes. However, there's a way around it, which is to introduce things called spin C structures, which essentially means that if you are willing to introduce abelian gauge fields into your problem, you can always get round obstructions to the existence of a spin bundle, which is what we're talking about here. provided you are orientable.
Does it also require it's not bounded? There's not a boundary on the space.
Boundary on the space-time, I don't think I care about boundaries.
Well, maybe you're going to remove singularity and you're left with a hole.
Yes, you can always do that.
But if you it means you can't get infinitely close to the boundary, because then you can't make, there's a direction you can't go in. You can't make Minkowski space out of that.
You obviously cannot get arbitrarily close to the boundary, so you probably want to cut a little. The question is, what do you actually want to remove when you remove singularities? Well, I don't know. I'm supposed to give a seminar about singularities in the Big Questions series on Thursday afternoons. And if you really want to know what happens at singularities, I suggest you come to that when I have sorted out what really happens at singularities. As far as anybody knows. The problems that we face with the existence of E are no worse than problems we face with the existence of the vector field or the metric field, any vector field. I mean, it's the same kind of problem. I don't think we should get too hung up on topological issues yet. It's all right to do it later, but not now. So the first thing is to see, next thing to do is to stare at this thing and realize that these things really have, well, you can see why the word bein appears here. E mu A has got two kinds of legs. It's got a space-time index and it's got a Minkowski space index, usually called a tangent space index. I also have two metrics in this problem. I have got GAB, the space-time metric, and I have got eta mu nu, the Minkowski space metric. So I have here the opportunity of raising and lowering both the space-time index and the tangent space index separately. These would be independent operations. So, for example, I can raise a tangent space index with eta. Like that. Eta mu nu is, of course, with its indices upstairs, the inverse of eta mu nu with its indices downstairs, but we all know that's the same thing. I can lower a tangent space index. Similarly, I can raise and lower space-time indices. I think I better do lowering first. And lastly, I can raise a space-time index using the inverse metric. Like that. And of course, you can just keep going like that forever. Now you can see, given the existence of such things, that general relativity has a hidden symmetry property, namely local Lorentz invariance. So we know that general relativity has already got a symmetry property, which is namely local coordinate invariance, but it's got another one, local Lorentz invariance. E A mu, if I give you one of these frame fields, I can transform it into E rho, no, write it this way, A equal to lambda mu rho E rho A. That's a transformation, which is effectively a Lorentz transformation carried out at a particular point on E. Now, that of course leaves eta mu nu unchanged. And the way to see that is just to stare at this defining expression here. If you write this thing out, this is the same thing as lambda mu rho, lambda nu sigma, E eta rho sigma. That's what you mean by a Lorentz transformation. So this is a definition of a Lorentz transformation. But this is the same thing as this. Whereas this thing, you see, is E mu A, E mu B. So this combination here, you see, is just as good a frame field as the original one, because lambda is a Lorentz transformation. So these frame fields are equivalent. Furthermore, this could be a function of position. If this thing is some weird function of position, it makes absolutely no difference, because in this expression there are no derivatives anywhere. So this could be a different Lorentz transformations at different points. And it still works. So this thing can depend on where you are. Hence, local Lorentz invariance, and not just the kind of global Lorentz invariance that you find in Minkowski space. For those of you who are following the supersymmetry course, I don't know how many of those there are here. Substantial number. Okay, so here is an unfortunate fact that you need to know. Most of the supersymmetry you have done is what's called global supersymmetry. The supersymmetry transformations are associated with a constant spinor field epsilon, which is the superpartner of a Lorentz transformation. The lesson from this is that in general relativity, you make Lorentz transformations local, not global, meaning they can depend on where you are. And a consequence of that is that if you try to consider the supersymmetric extension of that, you will also make your supersymmetries local. That's, in fact, the origin of supergravity theories. So supergravity theories start from this kind of consideration, but unfortunately we do not have time to do very much about it.
A theory with local Lorentz invariance, does that take up all the degrees of freedom of global coordinate transformation?
No, they're separate. Would you like me to count degrees of freedom? Let me do that. I wonder if I can do that and get it right. So, the usual way of counting degrees of freedom is to say that the metric has got degrees of freedom a half dd plus 1 in d dimensions, because it's a symmetric matrix. And the invariance property is that G goes to G plus del A psi B plus del B psi A plus higher order stuff, these being infinitesimal coordinate transformations of which there are D. The rule is you subtract off D, but then you subtract off D again because of the residual gauge transformations you have left if you try to fix the gauge. So that counts up the number of degrees of freedom in the gravitational field, and it's equal to a half D into D minus 3. Now you want me to do it for the E's. So the alternative way of describing the gravitational field is not to pick a metric, but to pick a collection of E's instead. I'm not sure I'm going to get this right, but I will try. So let's see, there are d squared different E's. There are still coordinate transformations, so I still need to subtract off 2d. There are Lorentz transformations of which there are half dd minus 1. So I subtract off 2d for the coordinate transformations and twice the dimensionality of the Lorentz group. So it looks to me as if I end up with d squared minus 2d minus d squared plus d, which I don't think is right. I shouldn't have fallen for this.
But as you said, if you can alternatively specify the E field, the E's, then surely that fills up all the...
I have specified these, or d squared of them.
Yeah, well, I mean, what else would you need to specify?
I think I know what I've done wrong. I think that you should only count the Lorentz transformations once because they're not dynamical. Let me try again, see if that works. So it's a half here and a half here. So I would get d squared minus a half d squared, so it's a half d squared. Minus 2d plus a half d is minus 3 halves of d, which does agree. So the point is the Lorentz transformations are not dynamical, they don't have residual degrees of freedom once you fix the gauge. That is the answer. So this is coordinate, and this is Lorentz. Now, where am I? Right. So after that slight digression, you might ask yourself about the covariant derivative operator. So here there's a slight problem. E a mu has got a space-time index that we understand how to take the covariant derivative of. But it also has a Lorentz index that is going to stop us understanding precisely what to do on the face of it. This thing will, of course, since it's a space-time index, behave in the usual way. This thing is basically a vector index reflecting the fact that under coordinate transformations, E transforms like a vector. But it also has non-trivial transformation properties under Lorentz transformations. So under Lorentz transformations, E transforms also like a vector. So if I'm going to invent the covariant derivative of something, say for example an expression that looks like that, I've got to ensure that it transforms like a vector, a tensor of type 1, 1 and a Lorentz vector. So the standard transformation rule that you know and love needs modification. Now, as you know, so that means you need to modify the idea of a connection to account for this. In general relativity, but not in supergravity, since we're not doing supergravity, we're not going to worry about this. You usually look at symmetric metric connections. So it will be very nice if it were the case that del E had nice properties consistent with the idea that G is associated with a symmetric metric connection, namely the covariant derivative of this is equal to 0. Now, a defining relationship for this thing here is that we describe the Minkowski space metric in terms of two E's and a G. But we can turn this expression round and try and write this as metric is equal to E A mu E B nu eta mu nu. At first sight that might seem a little incredible, but in actual fact you can see that this has got to be right, because if you contemplate this thing, eta mu nu we already know is E mu C E nu D G C D. Now let's look at this expression. E A mu E mu C is the same thing as E nu A E mu C eta mu nu. And this thing, well, because we can raise and lower indices with respect to eta, this is the same thing as E mu E nu A E C mu eta mu nu. That is the same thing as G C D E A nu E D mu eta mu nu. And this thing is the same thing as, well, that thing is just the metric again. So this is the same thing as G, C, D, G, D, A, which is the Kronecker delta of dA. CA, I mean. So this ringed combination of stuff here is the same thing as delta AC. Similarly, this stuff here, EB nu E nu D, must be the same thing as delta BD. And then you multiply it by GCD. And that is, as promised, the same thing as GAB. So, it would be very nice if the covariant derivative of this vanished. A convenient thing to do is to make the covariant derivative of the frame field vanish. That's not necessary, it is merely convenient. and consistent with the idea that the covariant derivative of the metric vanishes. So this is going to be consistent There is one potential step missing in this. I didn't tell you what del A of eta mu nu is. At first sight that looks terrible, but this thing, well, it's a Lorentz tensor, but of course it's a space-time scalar because it doesn't transform under space-time, under coordinate transformations. So this must be the same thing as this, more or less. And that is 0 because eta is constant. So equally I'm going to make that assumption. This should go in inverted commas. This, I emphasize, is a choice that I have made. It's like making the choice of a symmetric metric connection in general relativity, and in fact it is more or less the same, exactly the same kind of thing. It is for my convenience, it is not a law of nature. Okay. So now we can write down a formula for the covariant derivative of the frame field. A of E B mu is, well, this thing is a vector in space-time, so there will be a partial derivative term. Then there will be a connection term of the usual type. Just a minute. Now that, of course, has absolutely no guarantee whatsoever that it's equal to 0. So I'm going to add an extra term which makes it equal to 0. Omega mu nu A that's right. A E B nu. That's the term I want to add. This term here, you see, all I have done is linear algebra here. You can rewrite this thing as omega equals something. So this term here, the correction term, is usually referred to as the spin connection. So it's an extra bit which you've simply added in such a way as to make the covariant derivative of this thing equal to 0. That means that I can just simply solve for the spin connection. Looks like the next class is waiting already, so I better stop there. I can leave it as an exercise to solve for the spin connection.